Hello friends, welcome to another lecture of nuclear physics. In this video we are going to discuss about nuclear size and mirror nuclei method to estimate the nuclear size. Okay, so before we start, please do subscribe the channel, hit the thumbs up button. Also share with your friends, inspire me to create new contents for you and help me to grow my channel. So now let's start. And let me tell you one more thing. If you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT 123. This is my Insta ID. You can follow me on Insta. So now let's start. So first let us discuss about nuclear radius. Okay. So that means we are talking about nuclear size. So obviously it depends on the radius, right? So longer the radius, larger in size. That's it. Okay, now you see, we know that a nucleus contains protons and neutrons, right? Protons and neutrons. Okay, so this nucleus is supposed to be spherical in shape. Okay, spherical in shape, right? So it consists of protons and neutrons, right? We know that. So number of protons plus number of neutrons gives you mass number, right? So more number of protons and neutrons, larger in size, so that's why its volume must be proportional to the mass number, right? So now you see, so that's why we can write as the nucleus is supposed to be spherical of radius r and its volume is directly proportional to mass number, right? So here B is proportional to A is mass number, right? Mass number means number of protons plus number of neutrons, right? And as I have mentioned here, the nucleus is supposed to be spherical of radius r, so its volume must be 4/3 pi r cube proportional to A. So this part is constant, so we can write that r cube is proportional to A, so r must be proportional to A to the power 1/3. So if we put equal sign, then there must be a constant of proportionality, that should be r is equal to r naught A to the power 1/3. Here this r naught is called empirical constant, right? So its value is approximately 10 to the power minus 15 meter. Okay, so now you see here, okay, first let me mention this, what is r naught, that is empirical constant. Its value is approximately 10 to the power minus 15 meter, right? So now you see, so this is how we get radius of a nucleus. So let us discuss, a method to estimate the size of the nucleus. Actually there are different methods. Okay, So we're gonna discuss here in this video mirror nuclei method, right? Mirror nuclei method to estimate the size of or to estimate the radius of a nucleus. Okay, so now you see, what do you mean by mirror nuclei? So mirror nuclei means pair of nuclei obtained from each other by the interchange of neutron with proton, right? For example, let us take carbon 13. So just give me a second. So nitrogen 13 to carbon 13, in this case one positron, that is beta positive, should be emitted along with a neutrino. So here you see this carbon 13 here, this 13 is mass number and the 6 is the number of protons, right? So that means, so its mass number is 13 means and proton number is 6 means there must be 7 neutrons, number of neutrons must be 7, right? So again you see, if you interchange the number of protons and number of neutrons, then it will be 7 neutrons then 6 protons in that case. So if the number of protons is now 7, here it should be 7 and proton and 6 neutron, right? If the number of protons is 7, then it must be a nitrogen nucleus. So N13 7, this is number of protons, right? So now you see, so these two nuclei are called mirror nuclei. Okay, and here you see, due to conversion of proton to neutron, in this process positron and neutrino, emission of positron and neutrino takes place. Okay, so neutrino is a neutral particle. Neutrino is a neutral particle of negligible mass. So we can say mass of neutrino is almost 0, and this beta positive is nothing but positron, right? This is positron. Okay, now you see, let me take a new slide. You see, if Z be the atomic number of the daughter nuclei, atomic number of daughter nucleus, so that means you see, here you see, so we have obtained carbon from this nucleus, so carbon nucleus from this nitrogen nucleus, so that's why this is daughter nucleus and this is parent nucleus. Okay, so hope you have understood this. So if we consider that Z is the atomic number of the daughter nucleus. Now, now suppose you see, so this is the daughter nuclei Y, and this is the parent nucleus X, and atomic number of the daughter nucleus is Z, and its mass number is suppose A. In both cases, mass number is A. So let us suppose this is Z plus 1. Its atomic number is Z plus 1. Parent nucleus is Z plus 1. So this is positron and neutrino. Okay. Now you see, in this case, the energy density, sorry, not energy density, the difference in Coulomb energy. The difference in Coulomb energy of the mirror nuclei is del E C is equal to, that will be given by 3 by 5 1 by 4 pi epsilon naught E square then Z plus 1 whole square minus Z square. For the time being, just remember this formula. We will discuss in details when we will be discussing about semi-empirical formula. Okay, so now you see, if you simplify this, then what you're gonna have, then Z square will be cancelled, so we're gonna get 2Z plus 1, right? 2Z plus 1. Okay, now you see 2Z plus 1. Here you see, let me take this example. This is nitrogen 13 with number of protons 7, and this is carbon 13 with number of protons 6. So in this case, you see, this is Z plus 1 and this is Z, right? If you add these two, then you get 13, right? So 13, then this 13 can be written as this way also, 2 into 6 plus 1, right? So this is nothing but the mass number. Okay, so instead of this, we can write this formula in this way also, 3 by 5. So this term can be replaced by the mass number A E square by 4 pi epsilon naught, and A is the suppose mass number, right? If A is the mass number, so energy will be given by this difference in the difference in Coulomb energy will be given by this. Now you see, so this difference in Coulomb energies of these two nuclei is used to provide kinetic energy to this positron, and one part of energy is also used in conversion of proton to neutron, and to give rest mass energy to this positron. Okay, so that's why we can write that here you see, oh, I forgot to mention one more thing. There's supposed to be a R. I forgot to write that R. Okay, so let me write the R here. Okay, so here R is the radius of daughter nucleus, right? So now you see, this energy is spent in providing number one, rest mass energy, to produce positron, right, to produce positron. And number 2, let me write on the other side. Number 2, kinetic energy of the positron, that means this beta positive particle. And number 3, the rest mass energy required for conversion of neutron of larger mass, conversion of neutron of larger mass Mn, right, into a proton of smaller mass Mp. Okay, so hope you have understood this. So therefore we can write that this energy Coulomb energy difference is equal to, this is the rest mass energy of so let me write this rest mass energy to produce proton, let it be suppose m naught c square. Okay, and kinetic energy of the beta particle is suppose this positron is suppose Ke of, let me write this one as, okay, beta positive. And rest mass energy required for conversion of neutron of larger mass into proton is suppose that will be given by Mn minus Mp into c square. Okay, so that's why it can be written as m naught c square plus kinetic energy of this positron plus Mn minus Mp c square. Okay, so from this equation we can estimate, from this equation we can estimate the radius of a nucleus, right? So if we know the other values, then we can find the r, right? So hope you have understood this. So thank you for watching. See you in the next video. Bye bye.